Alrighty then. That little snippet was from Holst's The Planets again. That was Jupiter. Because today we are going to continue our discussion of planetary motion. Actually, we're going to show how Kepler's formulas for planetary motion led to the discovery of the universal law of gravity, law of universal gravitation. Newton was able to use Kepler's results to demonstrate that his theory of universal gravitation must be correct. So we're going to take a look at the milieu that Newton was living in when he formulated his law of gravity. Just a little refresher on some of the historical things we studied before. This is a drawing from one of Galileo's notebooks. Now keep in mind, Galileo was before Newton's time. In fact, Galileo died in the year that Newton was born. That's how I kind of keep track of their chronological ordering. And Galileo was a contemporary of Kepler. So Galileo was the first person to mathematically describe correctly the path of projectiles, that they follow a parabolic path. And Galileo had other ideas that tried to relate the motion of things on the Earth, and use some ideas that we have studied when you studied kinematics and when you studied Newton's laws, because Galileo is credited with the basic idea behind Newton's first law, the law of inertia. And then we saw a couple days ago, or yesterday, depending on when you're watching this, that Kepler was able to describe the orbit of planets. He had three laws, and the first law explained that the planets did not move in circles, which had before then been thought, but that they moved in elliptical paths, with the sun at one of the foci of the ellipse. Sun at one focus, I guess. So, the controversy that we talked about previously had mostly been settled by the time that Newton came along. As I said, Newton was after the time of Galileo, and by the time that Newton came along, it was generally accepted that the planets must be in a heliocentric system with the sun at the center and the Earth is just being another planet. But there was some other controversies then that came up with, well, if that's the case, what is it? Why do the planets follow these elliptical paths? What is it that keeps the planets along these paths around the sun? And we're going to see today how Newton used the discoveries of the people that came before him to comment about that. Newton was born, depending on what calendar you're using, he was either born on the 4th of January 1643 or on the 25th of December 1642. At Newton's time, England had not yet adopted the Gregorian calendar, and so they were keeping time with an older calendar. During Newton's lifetime, the calendar came to England, so his date of birth is more properly given in our current calendar as 4 January 1643, but in their calendar at the time, he was actually born on the 25th of December 1642. Now Newton was born, his father died before he was actually born. He was premature when he was born, premature birth. He was probably, if you were to describe him, whenever I think of Newton and his general disposition, we only know about it from his writings and people have written about him, but I think of somebody like Sheldon Cooper from The Big Bang Theory. You know, very brilliant, but somewhat off-putting. Not always, you know, the most personable person you could meet. He was kind of absent-minded. His mom, actually, his mom remarried when he was about 3 years old. And then she sent Isaac to live with his grandmother while she went to live in the household of her new husband. And so Isaac was, you know, raised on a farm and an estate there. But he wasn't much of a farmer. The story is told about one time he was sent to the market to see, you know, if he could get a good price for a cow that they had. And supposedly he came back from the market, and he was supposed to bring the cow back, I think, if he didn't sell it. But he didn't have the cow with him. He just had the halter, just the reins that the cow would be led with. And he didn't even realize he didn't have the cow with him. He just had the halter. So not exactly a brilliant farmer by any means, but he certainly found his ultimate calling there. He eventually got admitted to Cambridge. This is around the time of the Restoration, when the King Charles II was replaced on the throne. He was put back on the throne of England, and it's around the time of the plague, in fact, when Newton went to Cambridge. I believe it was shortly after he graduated with his bachelor's degree that they closed down Cambridge University because of the plague that hit London. They thought it would be best to not have so many students, you know, crowded together in a small school, you know, so close to a center of, you know, where the plague was occurring. And so he got sent home, and while he was home from the plague, it is said that he did a lot of the thinking about what would later become his Newton's laws and his theory of gravity. In fact, the famous story is told about how Newton thought about the law of gravity while watching an apple fall. Now, one of the versions of the story says the apple hit him on the head, but we don't think that's very likely. But it was also told supposedly a biographer of Newton said that he had been told that Newton happened to see an apple falling from a tree, and there were indeed apple trees in his grandmother's orchard there, which I believe is where he went back to. And he happened to see an apple fall from the tree at the same time as you could see the moon in the sky. And that caused him, so the story goes, to be thinking about how is the motion of the moon around the earth and the motion of an apple falling to the earth, are they different things, as everybody else thought, or could they in fact be manifestations of the same thing? As we're going to see, they are both manifestations of the same force of gravity. The same force that causes the apple to fall from the tree and hit the earth is indeed the force that causes the moon to go around the earth in its orbital path. In 1669, he became the Lucasian professor of mathematics at Cambridge. So the plagues happened in 1665 and 1666, and that's why he had been sent home and had some time to think there. When he became the Lucasian professor of mathematics, the Lucasian professor of mathematics is a very famous professorship at Cambridge. It is the other Lucasian professor of mathematics you may have heard of in history was Charles Babbage, who was one of the inventors of the ideas behind computing. He made the first programmable mechanical computer. And then Paul Dirac, who was one of the people that helped found the science of quantum mechanics. And then one you may have heard of is Stephen Hawking, who was, until just a few years ago, the Lucasian professor of mathematics who contributed a lot to the study of cosmology. Anyway, while he was a professor there, he was visited at one time by Edmund Halley. You may have heard of Halley's Comet, which comes back every, I think it's every 75 years or so, every 76 years, something like that. Halley was the first person to be able to accurately predict when the comet would come back, based on his understanding of the orbital mechanics. But Halley, his friend, persuaded him to publish some of the things that Newton had been writing. Now, keep in mind, Newton wrote about all kinds of things in his lifetime. He was certainly interested in things like alchemy. He wrote more about alchemy, which was a non-scientific version of chemistry, in which people tried to do things like find the Philosopher's Stone, or as it was called in the American version of Harry Potter, the Sorcerer's Stone, that would allow somebody to live forever, or to find a substance that could turn baser metals like lead into gold. Eventually, some of those investigations were helpful, and they did lead to chemistry. But Newton wrote a lot about that, and he wrote a lot about religion. Some of his religious ideas were unorthodox for the time, to say the least. But he wrote some small amount about the physics, and it's Newton's physics that is mostly lived on to today. He eventually published in, let me get the date right here. In 1687, he published what is known as his Principia. Full title is Philosophiae Naturalis Principia Mathematica, which means Mathematical Principles of Natural Philosophy. Keep in mind, at the time, natural philosophy is what they called physics. And this was a mathematical basis for physics that he was kind of trying to figure out. So let's look at some of Newton's contributions here. One is his explanation for why something like the moon could be in orbit if it was being attracted to the Earth. Here is a diagram from a later version of the Principia, showing what is known as Newton's canon. Now, we talked about orbits, orbital motion, we did circular paths, but it's worthwhile going back to it here. Imagine, Newton said, if you had a cannon mounted on top of a tall mountain, and that cannon fired a projectile. As I said before, Galileo figured out that the projectiles go in a parabolic path, and so if you fired your cannon with just a small speed, that projectile would take a path that would be like path D here. It's going to be largely parabolic. One of the things about this, though, that because the Earth curves away a little bit, it's going to go just a little bit farther than it would if the Earth was flat, because it can keep going, because the Earth is curving away from it, so it can keep going a little bit farther. And then, as Galileo figured out, if you fired it with a larger initial velocity in a horizontal direction, it would go a little bit farther. We saw that when we investigated projectiles. If you fired it even faster initially, it would go even farther. Eventually, if you fired it fast enough, it would have enough speed that its horizontal motion forward would make up for the fact that it's constantly falling. So even though the cannonball is constantly falling towards the Earth, it never gets any closer to the Earth because the Earth is curving away underneath it. And so it can keep going in this circular path all the way around the Earth. And that's what an orbit is, according to Newton. So, in other words, what Newton was able to show was that there could be a relationship between those two motions, as I said. Perhaps when he was observing that apple falling from the tree at the same time as he was observing the moon in the sky, was his explanation that you could have something, one force that would account for the fall of the apple and the orbit of the moon, and in fact the orbit of all the planets around the sun. This has been an idea that has been percolating, well, perhaps before Galileo, but certainly in Galileo's time. As we talked about before, Galileo discovered things like sunspots on the sun and small moons orbiting around Jupiter. So Galileo showed that things that are happening in the heavens are not necessarily perfect and unchanging. They could be similar to things that happen here on the Earth. And Newton was the first person to give a mathematical explanation for that, how something as simple as an apple falling could be related to the motion of the moon. So maybe the things that happen in the heavens are not so different from the things that happen here on the Earth after all. So let's go ahead and take a look at how one could derive Newton's law of gravity from Kepler's third law and our knowledge of circular motion. So we're going to use a circular path here. You don't have this with a circular path. It works for a general elliptical path, which is what Newton knew that the planets moved in. But let's derive Newton's law of gravity from just taking something, a planet going around the sun, such as the Earth, because the Earth has an almost circular path. So we have a planet going around the sun in a circular path, and let us take Kepler's third law for that then, and apply it using our knowledge of circular motion and see what we can come up with. This is kind of what Newton did when he derived his law of gravity. So we know that if something is going to be in orbit, traveling around in a circular path, it must have an acceleration towards the center equal to its speed squared divided by the radius of its orbit. Now, for the speed, let's put in the speed is the distance it travels divided by the time it takes to travel that far. So let's put in for the speed, let's put in the distance it travels, which is in one path around the sun, 1 year for this planet, it's going to travel a distance of one circumference, which is 2 pi times the radius. So if we substitute for v, we substitute in 2 pi. If v is equal to 2 pi r divided by the period. So this is the radius of a circular orbit, and this is the period, time it takes to go around once. If we put that in that formula, then we get this over here. The centripetal acceleration must be 4 pi squared times r over t squared. Now Kepler's third law says that for planets going around the sun, there is a relationship between the period and the radius of the orbit. Again, we're using circular orbits to make it easy on ourselves, so the radius is, we can use the radius instead of worrying about the semi-major axis here. So t squared is some constant times r cubed is Kepler's third law. Well, we can, in that formula there, we have r, and we have t squared in the denominator. So for t squared, let us plug into here, let us plug in cr cubed down here. And so that's going to give us t squared, we're going to say instead cr cubed. And this r will cancel with one of these, making it r squared. And so what we're left with is, for a circular orbit of a planet anyway, the acceleration is equal to 4 pi squared over c times 1 over r squared. Now I think you might be able to see kind of where this is going. It's 1 over r squared. That's our inverse square dependence that shows up in the law of gravity, as you learned last year in Physics 1, or whenever you took Physics 1. Now there was quite a debate about why would it be r squared? Isn't it just, if there is some force, and this force is what causes these planets to go around the sun, does that force diminish with distance? Well, yes, it has to. As we see here, the acceleration gets less with distance, so the force causing that acceleration must get less with distance. But how does it get less with distance? Is it 1 over r, or is it 1 over r squared, or some other number? Well, here, Newton, just using Kepler's third law, showed that it's a 1 over r squared dependence. You can also use that 1 over r squared dependence to show that the path of a planet around the sun must be an ellipse. So he's also able to show that. So using Newton's second law, that the force is equal to the mass of the planet times the acceleration, we now have that the force of gravity of the sun on this planet must be a bunch of things that are constant times the mass of the planet over r squared. Now, Newton realized that the formula must be symmetric. The force of the sun on the planet must be the same as the force of the planet on the sun, because he had Newton's third law, which meant that the formula, whatever the formula for the force of gravity must be, it must not distinguish between the sun and the planet, because the force that you get out of it must be the same. So it can't have, the force of one thing in the numerator, mass of one thing in the numerator perhaps, and the mass of the other thing in the denominator. That would not be symmetric. If you reversed the two things, you'd get a different amount of force. And so Newton said that the force of the sun on the planet, which we call the law of planetary gravitation, must be some other constant, and we'll absorb all these constants here into that constant. We're going to factor out of this constant here the mass of the sun to make our formula symmetric now. So now we get the same force using the same formula if you're calculating the force of the first thing, which is the sun, on the second thing you mentioned, which is the planet, or if you mention the force of the planet on the sun, you get the same amount, even if you reverse those two things, because multiplication is commutative. And so we get basically that. Now here is the genius of Newton. He was able to say that, as Galileo showed with some of his demonstrations and things, perhaps things in the heavens are not as different as what we think. Perhaps things in the heavens are not always, perfect and immutable, unchanging, as Galileo showed. And so Newton took the final step here. He said, this force here, this force that tells us how strongly the planet is being pulled by the sun, and, according to the third law, how strongly the sun is being pulled by the planet, that force is not just between planets and suns, it is between any two things. So this is what we call Newton's law of gravity, or Newton's law of universal gravitation. Universal meaning everything in our universe that has mass attracts everything else in our universe that also has mass. And so the formula is the magnitude of the force of gravity is some constant times the mass of the first object times the mass of the second object divided by the distance between the two objects squared. And if their objects have some size to them, well then this is the center of gravity of the two objects. Each object has a center of gravity in it that determines where all the force of gravity can be said to act on it. For a sphere, it's just like from the center of one sphere to the center of the other. That's often what we do. So that gives us the strength of the force of gravity, and then the direction is always in the direction of the other object. So the force on mass 2 caused by mass 1 is going to be from mass 2 to mass 1. Gravity is always an attractive force. You'll learn about in the next semester, if you haven't already taken Physics 2, you'll learn about the electric force, which can be attractive and repulsive, but it's very similar in formula to this. Let's do a couple of practice problems here. Find the gravitational force exerted on the moon, which has a mass of 7.36 times 10 to the 22 kilograms by the Earth, which has a mass of 5.98 times 10 to the 24 kilograms, when the distance between them is 3.84 times 10 to the 8. Well, you can go ahead and work on that one. I'm going to go ahead and do it on my calculator here as a way of timing about how long it will take you to finish it. Of course, most of you are faster than I am. That G, that universal gravitational constant, it is listed on your table of information. It is a very small number because the force of gravity is a very weak force. The number there it is. G is equal to 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. Now, it took a long time to get that value. Newton just talked about proportionalities. He didn't really refer to the actual numerical value of it. And it's not easy to do because you can predict the relative magnitude of the force if you know the mass of, say, the mass of the sun or the mass of the earth, or the mass of the moon and the mass of the earth, but we don't know those masses inherently. We have to guess them. Now you can get, if you know the mass of the earth, then you can get this constant because you can get what the gravitational field strength, as we call it, 9.8 newtons per kilogram. Using that number, you can find out what the mass of the earth would be if you know G. Or on the other hand, if you know G, then you can find out what the mass of the earth would be. We'll talk about that one in just a minute. Let's go ahead and do this one calculation and then we'll maybe come back to that. So we say 6.67 second function EE minus 11 times 7.36 second function EE22 times 5.98 second function EE24 divided by 3.84 second function EE8 squared. And the answer is 2 times 10 to the 20 newtons. Force of the Earth on the moon is equal to 2 times 10 to the 20 newtons. There we go. There was as I said, I think we'll talk about the gravitational field strength and that G and using that in the later on in the week. For right now, let's just see how they did actually measure G. If you have to know the mass of the Earth, let us say, to find G, well, they could estimate the mass of the Earth. They know the Earth is made out of rock. This is how the estimate was made. And if it's made out of rock, well, how much does rock weigh per cubic meter? And what's the density of rock? And if you know the density of rock, then you can estimate the mass of the Earth, because you know the volume of the Earth. The radius of the Earth is pretty easily found. The ancient Greeks knew that number, more or less. But if you do that, you're assuming that the Earth is uniform. First, you're assuming it's a sphere, which it turns out it's not quite. But more importantly, you're assuming that every part of the Earth has the same density, and it doesn't. So there was, Cavendish was able to figure out, using a very subtle experiment involving large masses. You see, this force is very small for normal-sized things. If you talk about the Earth on a person, well, okay, it's a few hundred pounds. If you talk about, though, one person, gravitational force on another person, it's pretty small, because neither of them have a big mass, big enough to make this number appreciably large. But Cavendish figured out how to do it. He had an apparatus that had spheres like that, and then another set of spheres attached to rods that go like that, and this set of spheres attached to a lighter spheres, but also attached to rods. This apparatus was kind of free to move, at least this part of it was free to move, kind of like a mobile. And so this sphere protected that sphere, and this sphere protected that sphere, and it would move slightly. And by measuring that motion, and the way he did it, he used a little mirror right here, and shined light in that mirror, and by showing where the reflection of that light, as it moved across the screen that was some distance away, he was able to see how much this apparatus shifted in its position over a period of time, and from that was able to figure out how much the force of gravity must be, given the exact mass of these two things, then was able to figure out what G must be. And that's not the way they said it, they didn't say it in that form, but he was able to essentially figure out how much the mass of the Earth must be, because if you know what G is, you know the mass of the Earth. So some people say he weighed the Earth. Maybe that's a long time after Newton. Newton just had the ideas of what the force was proportional to. There's a couple other problems in here. I'm not going to bother working through them. There's another one here. Gravitational force between 65 kilogram person and a 50 kilogram person when they're 0.5 meters apart. Just plug and chug. If you want some practice, this one comes out to be 8.67 times 10 to the minus 7 newtons. Oh, and I do have that thing about figuring out G, little g, if you know big G. So we can go ahead and do that one now. I'll talk more about this idea of this gravitational field strength later on in the week, but we know that the force of gravity on something near the surface of a planet, like say the Earth, is the mass times little g. Well, the force of gravity, though, must be equal to big G times the mass of, say, the Earth times the mass of the object divided by the distance between those two squared. We take the center of the Earth as where its gravity is said to act. So the distance then is just the radius of the planet. So if we know the radius of the planet, the radius of the Earth is 6,370 kilometers. Well, this is times the radius of the planet squared. Which means that G, little g, must be equal to all of this. Because all of this times m is equal to the force of gravity. Let's find the mass of the Earth then. We know that G is going to be equal to 9.81. And that should equal to big G times the mass of the Earth divided by the radius of the Earth squared. So therefore, the radius of the Earth squared times G divided by big G must equal the mass of the Earth. Let's see how close we got to that number that we gave a moment ago. We're going to use G is equal to 9.81 because that's the worldwide average there. So we'll say 6370 times 10 to the 3 meters squared. So 6370, second function EE, 3, that's the radius, squared, times 9.81, divided by, and G was, as I said before, 6.67, second function EE minus 11. And the answer I get is 5.9 6.96, so 6.0 times 10 to the 24 kilograms. And I think a moment ago, we said 5.98 times 10 to the 24 kilograms, so about the same number. All right, in the next class, we're going to talk about the idea of gravitational potential energy, but we're going to be more general about it than just the formula we've used so far, which is near the surface of the planet, what the gravitational potential energy is. We're going to derive that potential energy formula, and then we're going to use it to solve some problems.